Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. Today, let us do a deep dive into a very important topic, electric field lines from the unit electric charges and fields. Our goal is to make sure we grasp this visualization tool simply and safely for our exams. So students, we've already established that the electric field is, well, it's invisible. It's a region of influence around any charge, and it's a vector. That means it has both a magnitude and a direction at every single point in space.
Which sounds incredibly complicated to map out.
It is. It poses a real challenge. How do physicists or, say, engineers even begin to visualize this invisible electrical environment? I mean, if you want to design something complex like a particle accelerator, you need a mental map.
That is the essential question, isn't it? If the field is invisible and it's everywhere, how can we possibly make sense of it visually? If we just tried to draw little arrows at every point, it would just be chaos, a complete mess.
Exactly. Chaos is the problem. And this is where the idea of field lines becomes really, really interesting. You might naturally assume that if we are drawing lines on a map, they should be evenly spaced, like grid lines on graph paper.
Yes, that would seem logical. Uniform.
But the surprising and sort of counterintuitive fact is that the spacing of these field lines, it's variable. And this non-uniform spacing is the whole key to their usefulness.
So we're not just mapping the direction, but the strength is somehow hidden in the gaps between the lines.
Precisely. The density of the lines conveys information about the field strength. Where the lines are drawn very close together, tightly packed, the electric field is strong. And where they spread far apart, the field is weak. It's like a contour map for electric force.
Oh, I see.
This technique is absolutely indispensable. For example, in something like a particle accelerator, engineers need to control charged particles with extreme precision. So they will design the equipment specifically so that the field lines get bunched up, they converge in a certain region. When those lines converge, the field is strongest, and the particles get a maximum targeted push. The whole design relies on interpreting this non-uniform spacing.
That's actually quite clever.
It is. So, okay, let us go back to the core idea. At their heart, electric field lines are purely imaginary curves. They are just a visual representation. A teaching tool, really, that helps us map this invisible field. The brilliant part is that they show us both direction and strength at the same time.
Okay, so how do we visualize that?
Let's use a very good analogy. Think of water flow lines or streamlines. Imagine you're looking down at a stream and there's a big boulder in the middle of it. You can see the lines the water follows, right?
It's flowing around the rock.
Now look closely. Where the water has to squeeze through the narrow gap right next to the rock, the streamlines bunch together. That tells you the water's flowing fastest there. The flow is strongest. Then downstream, where the water spreads out, the lines also spread out, showing the flow is slower.
So the field lines work just like that. They show a flow pattern for the electric field, and the speed is like the field's strength.
That is the perfect way to think about it. Now, why did Michael Faraday even need to invent this? Well, because, as we said, the field is a vector at every single point, describing that mathematically everywhere. It's just too complex.
Yeah.
Field lines give us a simple, visual language to quickly assess the situation.
Okay, but if they are like water streamlines, which are the actual paths the water takes, does that mean a charged particle would follow the electric field line exactly?
That is an excellent question, and it's probably the most important misconception we need to clear up. For now, the answer is generally no. We will come back to exactly why later. But first, remember, they are purely visual tools, not physical paths.
Okay, visual tools. Got it.
So, to complete our mental image, imagine a positive charge as a tiny sun. The field lines are like rays of light radiating outward from it in all directions. They point outward, away from the positive charge. And as these rays spread out, their density decreases. This beautifully shows us that the field gets weaker as you move further away.
And a negative charge.
It's the exact opposite. Picture it like a sink or a tiny black hole absorbing light. The field lines point inward from all directions, gathering density as they get closer to the charge. So that single image, the sun and the sink, it captures both the direction and the changing strength. All right, now that we have the intuition, let's get a bit more formal for the exams. We need to see how the insert textbook defines this. This is very important for writing proper answers. Could you please read the formal definition from the source material for us?
Yes. The insert definition states, an electric field line is, in general, a curve whose tangent at each point is parallel to the electric field vector at that point.
Excellent. That one sentence is the foundation. Let's unpack that key phrase, whose tangent at each point is parallel to the electric field vector. What it means is if you pick any point on that curved field line and draw a short straight line that just touches the curve there, that straight line, the tangent, shows you the direction of the electric field at that one exact spot.
So even if the field line is curving over a long distance, the force at any single point is straight along the tangent.
That is the crucial distinction. Now, from this definition, we get 4 essential properties. Think of them as Faraday's iron rules. You often get questions on these. Rule 1 is direction, just as we said. The electric field vector, E, at any point, is tangent to the field line passing through it.
Okay.
Rule 2, source and sink. Field lines must always start from a positive charge, that's the source, and end on a negative charge, the sink. Very importantly, they never form closed loops.
Right, I remember that's different from magnetic field lines.
Yes. If there's only one charge, say a single positive one, the lines start there and just extend out to infinity. Rule 3 is continuity. Field lines are always continuous curves. They don't have sudden breaks. The electric field exists everywhere, so its map must also be continuous.
That makes sense.
And finally, Rule 4, which is non-crossing. 2 field lines can never, ever cross each other. This is a very common point of confusion. Can you remember why?
Because if they crossed at that single point of intersection, the field would have 2 different directions at the same time, which is impossible.
Exactly. A physical and mathematical absurdity. The field must have a unique single direction at any given point. And finally, let's just make the strength part more precise. The density of lines indicates the field strength. Quantitatively, we define it as the number of field lines passing per unit cross-sectional area held perpendicular to the lines.
What does perpendicular unit cross-sectional area mean visually?
Good question. Imagine you have a tiny square frame, say 1 centimeter by 1 centimeter.
Yeah.
You have to hold that frame so the field lines pass straight through it like arrows through a target. Then you just count how many lines go through your little frame. Where the lines are crowded, your count will be high, strong field. Where they are spread out, your count will be low, weak field. That count is the density. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. So let's use these rules to quickly sketch the classic example, the electric dipole. You absolutely must know how to draw this. We have a positive charge, plus Q, and a negative charge, minus Q, near each other. The field lines will start on the plus Q, curve through space, and end on the minus Q.
Okay.
Now notice 3 things. 1, the lines point away from positive and toward negative. That follows our rules. 2, the lines are most dense, most crowded in the region directly between the 2 charges. This tells us the field is strongest there. And 3, the whole pattern is symmetrical. It's a beautiful visual summary of the entire field.
So the drawing itself contains all that information.
Exactly. And understanding these field lines is the bridge to our next big topic, which is electric flux. Flux is nothing but the mathematical way to count these lines. It answers the question, how many field lines are passing through this specific surface? And that idea leads us directly to the very powerful Gauss's law. Now, students, let us address 3 common errors. We can call them silent killers because they can cost you marks even if you think you understand the topic. Silent killer number 1 is confusing the visualization with reality. Students sometimes think the lines themselves are real physical things, like invisible strings.
Right, that they actually exist in space.
The correction is to remember. The electric field is real, but the lines we draw are just a man-made map. They are a purely mathematical tool to help our brains understand the real field.
So field is real, lines are a drawing.
Memorize that. Silent killer number 2 is the one you asked about. Confusing field lines with particle trajectories. The wrong idea is that a particle will surf along the field line. The correction is this. The line's tangent only shows the direction of the force at that instant. A particle has inertia, it has momentum. So its actual path depends on that force and its own initial velocity. Generally, the path will be different from the field line.
I see. So the tangent is just the direction of the push at that moment, but the particle's own motion makes it curve differently.
Precisely. And silent killer number 3 is a sketching error, drawing 2 field lines that cross each other. The correction is a reinforcement of Rule 4. Never, ever let them cross. If you are asked why, you must state that if they did, the field would have 2 directions at one point, which is physically impossible.
Okay, that's a very absolute rule.
It is. Now, to make sure this stays with you forever, let's create some memory anchors. We can use a simple mnemonic. Just remember LDT for electric field lines, L for lines are imaginary, D for density, which indicates strength, and T for tangent, which gives the direction.
LDT lines, density, tangent.
Okay, and an anchor phrase you can use is, field lines are Faraday's map. They show direction via the tangent and strength via the density. And finally, a physical gesture. Point your finger outward from the palm of your other hand, which is your positive source charge. Now trace a smooth curve in the air. As you do, keep your fingers crowded together near your palm, and then let them spread far apart as you move your hand away. This motion helps you feel the idea of decreasing density and field strength.
That's a good way to remember it.
So let us conclude this deep dive with 3 essential factual points for your examination. 1. Field lines are imaginary curves. The tangent at any point gives the direction of the electric field vector, E2. They start at positive charges and end at negative charges. They're continuous, and they never ever form closed loops. And 3. The density of the field lines is directly proportional to the field strength, and critically, field lines never cross each other. If you wish to build this kind of deep conceptual clarity and get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROF-SAM.
PROSSAM.com. Thank you for joining this deep dive. Keep studying, and we wish you the very best.